Hi, and welcome back to a new lecture from Computer Vision from Scratch. Today, we'll be implementing ResNet, which is one of the most popular convolutional neural network architectures. We will discuss about vanishing gradient, which was a very challenging issue faced by the deep learning community until 2015, and how ResNet solved this problem forever. We will also be discussing about implementation of ResNet and comparison of results with ResNet, VGG, SqueezeNet, and LXNet, which we have been implementing in this course till now. We'll compare all the results and see how ResNet performs compared to other convolutional neural network architecture. With that, let's get into the course. So there was a problem that deep learning community was facing. Initially, when LXNet introduced deep neural network for training on image-based dataset in 2012, and when they successfully showed that you can actually train deeper neural networks by also simultaneously implementing ReLU activation, regularization techniques, etc., and also GPU-based computing, it was actually a revolution. But when the community was trying to implement models with bigger and bigger layers, so LXNet had 8 layers, VGG had 16 layers, Inception V1, which was introduced by Google, also called as Google Net in 2014, it had 22 layers. And then people were trying deeper and deeper neural networks because they knew that deep neural networks could learn more features from the image-based data. But the problem was that it was very difficult to train these deep neural networks. If you remember, so far in this course, we have tried LXNet, VGG, and Inception. The best accuracy that we have got so far is for LXNet. In the last lecture, we tried SqueezeNet, which had really good accuracy, but SqueezeNet was anyway an altogether different CNN model. But if you compare the deeper and deeper neural networks, it was kind of counterintuitive to learn that deeper neural networks, for some reason, was performing worse, meaning we were finding it difficult to train. For VGG and Inception, we saw that validation accuracy was bigger than training accuracy. So sort of under training was happening. Overfitting was not happening, sort of like underfitting or under training was happening. So this was a bit counterintuitive, and deeper models were breaking everything. It was not working. But logic tells us that somehow deeper neural networks should be able to learn more things, right? But the problem was when you have deep neural networks, the initial layers in the neural network, like these are the initial layers, so input layer, and this you can call as the initial layer, and later layers, which are closer and closer towards the output layer, you can call as the more and more deeper layers. But these shallow initial layers, they hardly got updated. The weights and biases in these layers hardly got updated in the gradient descent training process. So we'll discuss how this issue is mathematically happening. We will see what did ResNet do something specially to solve this issue, and how it changed the course of deep learning altogether, and how it completely transformed and revolutionized image processing using deep neural networks. So with that, let's actually get into the lecture. The vanishing gradient issue was so big that even when you perform with good initialization parameters, even when you perform batch normalization or train for more number of epochs, sometimes this issue persisted. So before we look at the ResNet architecture, let's do a brief recap as we do usually. What we have been doing so far in this course, so that even if you are starting this course at this lecture, ideally you should be able to understand to some extent what has been going on. So we are trying to classify the 5-flower dataset. There is daisy, dandelion, roses, sunflowers, and tulips. There are 1,000 images in each of the classes, so it's a 5-class classification problem. We started with the simplest architecture, which was a linear model. So we started with RGB images converted into a flattened layer. In the output layer, there were 5 nodes because we are performing 5-class classification, but we did not have any activation function. We did use softmax activation at the last layer, just to convert the output numbers into a probability distribution. This resulted in 40-45% accuracy with a loss of 10 to 20. Accuracy was not so bad, but also not so great, because this is even a random classifier can give you 20% accuracy. This was 40-45%. This was training accuracy, by the way. Validation accuracy was 35-40%. Then we thought, okay, let's add a hidden layer with 128 nodes with ReLU activation. It did not change the accuracy much, but it decrease the loss by an order of magnitude. Here, the reason why this decrease was happening, which was a bit counterintuitive, was because the predictions were becoming more and more confident. So this was a good thing, but we were not happy. Then we thought, okay, there is some overfitting happening because validation accuracy is 35-40, training is 40-45, sometimes 50. So clearly there is a difference in validation and training accuracy. So we thought, let's add regularization, batch normalization, dropout, early stopping of epochs, etc. So we thought this might help, and it indeed helped to some extent. We would improve the validation accuracy to 50-60%, but we were not happy. That's when we realized that we have been training from scratch. So we should be training from, instead of training from scratch, we should be performing transfer learning, where we use pre-trained neural networks. So we actually tried ResNet model in the transfer learning initially, and this was for 10 epochs. And we got 100% training accuracy and 80% validation accuracy. This was okay, but overfitting was happening. That's the reason why there was a huge difference in training and validation accuracy. Then we thought, okay, now let's start step by step. Maybe we should go in chronological order, because start with the earliest of CNNs and then go with increasing complexity and see how well the classification will improve when we are performing it on the same data set. So we had the 5 flowers data set throughout. We started with AlexNet, the legendary paper that transformed deep learning forever, by Alex, who was the first author after whom the paper is named, Professor Geoffrey Hinton, who was the 2024 Nobel Prize winner in physics for the introduction of neural networks, and Ilya Sutskever, who was also the OpenAI co-founder. This paper is so amazing. It's been cited 170,000 times. So we ran for 10 epochs. We got 90% validation and 95% training accuracy. We became extremely happy. This was the first time in this course we received such a good level of accuracy without too much overfitting. And then we switched to VGG, and VGG had more number of parameters. It had exactly 138 million parameters. The AlexNet had around 60 million parameters. So VGG was significantly bigger. And even though we ran for 50 epochs using VGG, we got only 75% training accuracy and surprisingly 85% validation accuracy, higher validation accuracy than training, which was kind of interesting because it showed that we were under training. But we did not want to run for more epochs because this itself was taking around 4 to 5 hours. Then we switched to GoogleNet, which was Inception V1, also called as Inception V1. And we ran for 50 epochs. We got decent accuracy. We got 87% in validation, 86% in training. I would say no overfitting is happening, but accuracy was not as high as what we got in AlexNet. Then in the last lecture, we switched to SqueezeNet, which had a very small number of parameters, less than 5 million parameters. And we realized that SqueezeNet for 50 epochs was performing even better than AlexNet for 10 epochs. So AlexNet had around 90-94% accuracy for validation and training respectively. SqueezeNet also had kind of similar performance. So this was the best model so far. I know that it's a bit apple to orange comparison because we are running for more number of epochs here, obviously. But we were happy for the fact that similar neural networks, which were deep in number of layers like GoogleNet or VGG, could not perform as good as this. So with SqueezeNet, we were very happy. But this is where we were at a juncture. And SqueezeNet was introduced so that neural networks could run on edge devices, right? On mobile phones, on IoT devices, or even maybe small Arduino microcontrollers. So neural networks should be able to run on not so high performance computing systems. But ResNet did something different. ResNet solved a different problem. It was not solving the problem of compressing the model, but it solved the problem of being able to train big models. So what was happening was in the year 2015, 2014, bigger and bigger models started to perform not so great compared to smaller models. So that was a concern, and ResNet, the people who brought ResNet into the world, they wanted to solve it. So we'll discuss that. But before we enter into the lecture, something that we always do, I really want to remind you that starting a course or starting anything is very easy. Finishing is not at all. As you can see from this graph, the number of viewers is decreasing with the lectures proceeding. So if you are listening to me in this lecture, currently we are at the 13th lecture. If you are counting the lecture 0, You have come a long way, and I think this is a very, very good thing. So let's take a pledge, as we always do, lecture after lecture, that we will finish what we have started, because there is a reason we are all serious about doing this properly. So let's take a pledge. If you have a friend or acquaintance with whom you would like to learn computer vision, keep each other accountable, or feel free to put a comment which will make you publicly accountable. Now, with that, let's look at what exactly is this vanishing gradient problem in deep neural networks. In deeper and deeper neural networks, during backpropagation, there is a tendency for the gradients values to shrink exponentially. What this means is the early layers like layer 1, layer 2, etc., they will barely get updated in deep neural networks. So these layers are also called as shallow layers. The first few convolutional layers are shallow layers. And what this means is if they don't get updated, the model will not learn much, because those convolutional layers are the ones that are super critical for detecting edges, textures, shapes, etc. in images. So if the shallow layers are not optimally trained such that their weights and biases are perfect, you will not have a very good neural network, irrespective of how deep your neural network is. So the gradient updation process should ensure that the dough by dough So the gradient updation process should ensure that there is significant change happening to the weights and biases of these initial layers. So this results in a phenomenon that we have seen in the VGG lecture as well as in the Google Net lecture, that it results in something not overfitting, but something more like undertraining or underfitting, where validation accuracy is above the training accuracy. The part of the reason why validation accuracy was bigger was because we were using pre-trained weights, and we are using natural images, right? Images of flowers which naturally occur, which are very similar to the kind of images used in the ImageNet. And the pre-training of these models like VGG or pre-trained GoogleNet, the ones which we were using, were all trained on ImageNet dataset. So the pre-trained weights were so good that even in the absence of proper training, validation accuracy was pretty good. But this was not good, because we want training accuracy to be as high as possible, and without overfitting, we need good validation accuracy, but that was not happening. So the mathematical reason why this vanishing gradient happens is because think about the kind of activation functions that we use. We have tanh, we have sigmoid, sometimes we have ReLU. But if we are using sigmoid or tanh in between layers, look at the slope of sigmoid. So this is the plot of sigmoid. X-axis runs from -infinity to infinity, y-axis from 0 to 1. The maximum value of the slope of sigmoid is 0.25, and that occurs at x equal to 0. Now imagine we are performing dough by dough weights of the loss. So we have loss happening at the end because predicted output and actual output have some difference. Actual value that you are supposed to predict have difference, so that results in loss. And now we want to modify the weights. Either we have to increase some weights or we have to decrease those such that loss is decreased. So we want to move in a direction such that loss is decreasing. So we first calculate dough loss by dough weight. But to do this, if the weights are in the earlier layers, we do something called as we use something called as chain rule. So here chain rule, you can see that dough loss by dough activation after nth layer, dough activation after nth layer divided by dough activation after n-1th layer. And this one is dough activation of n-1 layer divided by dough activation after n-2 layer, like that. So you backpropagate using the chain rule all the way till the first layer or whichever layer you're looking at. Now, what this means is if your gradient of the activation, or if the rate of change of a function after performing sigmoid activation can only be max 0.25, then essentially when you perform chain rule like this till the initial layers, you are multiplying values which are lesser than 0.25 or between 0 to 0.25 many number of times. You may multiply 0.25 multiplied by 0.25 multiplied by 0.25 again and again and again. And this results in a gradient like dou L by dou W, which is very small. Because if you multiply a number less than 1 many times, you will get a resultant number that is very small, close to 0. So this results in a gradient that almost shrinks to zero in the early layers. This is not a problem for later layers, because in the later layers, you are not multiplying these many number of gradients in the chain rule. So for later layers, yes, modification for weights and biases will happen. But for the early layers, the shallow layers, layer number 1, layer number 2, etc., the gradient will not reach there. So this is called as vanishing gradient, and this is a problem for deep neural networks. This is a plot from a paper that demonstrates when you have a 56-layer neural network versus 20-layer neural network. Even when you run for more number of iterations, you have bigger training error for 56-layer neural network because of the vanishing gradient problem. And this plot again shows just a visual demonstration of how the magnitude of gradient looks like from first layer to output layer. Output layer will have higher gradient in general. Initial layers, layer number 1, 2, 3, etc., will have lower magnitude of gradients. So this is the gradient descent visualized. So let's see how ResNet solved this problem. The paper on ResNet was published by a set of researchers. One of the researcher is Kai-Ming He. He's a professor at MIT. And the paper currently, the original ResNet paper currently has 279,000 citations. This is a huge number by any metric. And ResNet absolutely shattered all the other models which were introduced up until that point. So what was the breakthrough that allowed ResNet to do this? Basically, they introduced the idea of residual connections, where they propose that if you have X as the input and let's say H of X as the output, instead of neural network trying to learn a mapping from X to H of X, the neural network will try to learn this residual F of X. So instead of the neural network learning the whole mapping, which maps from the input to output, it just tries to learn the difference between the output and input. So this difference is called as the residual. And learning this residual, it's a simple concept, but when you look at the neural network architecture, which I will show you in a moment, you will understand how this enables gradients to not vanish in the initial layers. So this paper by Kai-Ming He and others in 2015, although here it shows 2016, I think originally the concept was introduced in 2015 at Microsoft Research originally. And what they did is, instead of the layer learning the entire transformation from output to input, it will simply learn the difference between output and input. So this is the idea of skip connection. So you have layer 1 and layer 2 here. In between, you have activation. And let's say this is the architecture of whatever network you have. Let's not call it neural network yet, but let's call this as one residual skip connection module. You have X as the input, and instead of this module learning directly H of X, it will learn F of X, where if you add X and F of X, here you are adding X and F of X, you will get X plus F of X, which is equal to H of X. Now this H of X is the value that you are supposed to predict, but the actual prediction is happening here. This skip connection is just simply an addition of the input to the actual prediction that is happening. But because this skip connection exists, it doesn't matter how many such modules are there. You can almost always have a direct connection from the input layer to the output layer. So see, here the skip connection will ensure that this value at the input is directly reaching here. And here again, at the output, just see the value at the input is reaching the output here in the form of X. And if you are looking at an image processing using convolutional neural network with a skip connection, the values at the input has a direct influence at the output because of the presence of these skip connections. And this also ensures that whatever small changes happen here will have a huge influence on the output. And what does that mean? It means the loss is significantly influenced by the weights in the initial layers. And that indirectly means that you are not having a vanishing gradient, but you are having a good gradient, even in the early shallow layers. So this was the idea behind the ResNet architecture, which allowed them to completely redefine the field of deep learning. And based on this idea, many ResNet architectures were proposed, and some architectures had 100 plus layers, which was unthinkable. Like, it was extremely difficult to train a neural network with 100 layers. We already saw that with VGG with just 16 layers. It was extremely hard to train the VGG model with 16 layers, and the training accuracy was not increasing. Validation accuracy was already good because of the pre-training. So this is something that we have already experienced in this course. But the idea of skip connection we'll see in today's lecture when we implement ResNet 50 for the 5 flowers dataset. We will see how well the training can happen and how does the validation accuracy compare to the training accuracy. In 2015, what ResNet accomplished is nothing short of amazing. So in the ImageNet competition, they placed first and they surpassed all the performance matrices that was achieved by all the models until that point. And ResNet 50 in that year had 50 layers. And later there was ResNet 101 and many other ResNet architectures introduced. And this was the first time when the researchers after AlexNet got a full confidence that you can go with deeper and deeper models instead of playing with, parallel processing with 1x1 convolution, 3x3 convolution, 5x5 convolution. Those things were being done in VGG, in GoogleNet or in SqueezeNet. But ResNet, the single idea was instead of playing with different convolution sizes or instead of keeping the convolution size the same, focus more on residual connections so that you can go with more depth and you can actually successfully train the initial layers. And if that can happen, the initial layers will capture the features because the convolution layers in the convolution filters in the shallow layers can capture local and global features. And eventually when a prediction is made, if the prediction is bad, you can easily change the weights of these initial layers because the gradient is not vanishing. And there were many other competitions in which ResNet delivered outstanding results. And ImageNet competition actually consists of images like this. It's part of the website called ImageNet. You can Google the ImageNet website. And they had a specific set of images on which the researchers could train, but the test images were not open to the public. So you have to submit the model and then they will see how well the testing accuracy is. Now, why is this residual connection such a big deal? Like logically, not mathematically, why would residual connection make it so easy to learn the features in an image? So think about this, a task like image enhancement. So in an image enhancement, you can use a neural network to input a blurry image and output a high resolution image, right? For this specific task, most of the information that is present in the output image is already there in the input image. So it's not like input image is a completely useless, noisy image. It actually maybe has 90% of the information that you need. So why would you train a neural network from scratch? Like, why would you want the neural network to entirely predict this high resolution output image rather than predicting the difference? So if you subtract the output from input, you get some kind of noise, right? But this difference is small. And if you can learn this difference, then you can simply add the difference to the blurred input image to get the high resolution output image. So for the specific task of image enhancement, here I hope you understand the significance of residual connections or learning the residual. So in ResNet, if you have a ResNet architecture that connects from the input blurred image to high resolution output image, every module in this residual connections are just learning the difference. What is the difference that I should add to this input image? What is the difference that I should add in this module to the previous output? And like that, add the differences sequentially to get the high resolution output image. Fairly simple idea, but makes total sense when you are thinking about a task like this. Of course, I know that you may have questions like, how is this helpful? How does this work when you are trying to perform a classification? Because finally in classification, you need a class prediction. You don't need the image as the output. So how does that work? We'll get into that. In ResNet, one thing you should note is that in one skip module, the dimension remains unchanged. So whatever is the dimension of x, then the dimension of f of x should also be same as x. Otherwise, you can't add f of x and x. So imagine x is an image. You are adding some kind of noise or some kind of difference to the image to create a modified or transformed image. Then if x is a 32 by 32 image, then f of x also has to be 32 by 32. Otherwise, you can't add f of x and x, right? So please note that dimension remains unchanged in one block of the ResNet. Now, you may have a question like, if dimensions remain unchanged in the ResNet block, how can you perform classification? Because let's say you are inputting an image of 32 by 32 size. In the final output layer, you might need just a 0 or 1 as the output, or like a softmax distribution as the output, right? So how do you do that? So this is where you should understand that between two different blocks, ResNet can have varying sizes through max pooling or any other operation that reduces the dimensionality. So here, if you look at the ResNet block here, the dimension throughout locally is constant. It's 56 by 56. But when you go from this block to this block, dimension has reduced to 28 by 28. Here it has reduced to 14 by 14. Here it has reduced to 7 by 7. Then you will have a fully connected layer, and then you can finally make a prediction, right? So this is how you go from image to maybe a softmax distribution, probability distribution at the output through different blocks of ResNet layers. Now, from one stage to another, as I mentioned, you can have change in dimension. So for example, if we are using a convolution operation where the stride is greater than 1. So if stride is 2, you can almost half the dimension. So if the dimension was 64 by 64, it can become 32 by 32. So the change in dimensions depend on what kind of convolution you use and between two blocks, whether you are performing a pooling operation or not, right? An interesting consequence of the residual skip connections in ResNet is that it can be also used as an Euler integration method. So in Euler method, we have something like this, right? We have a y equal to f of x, and we might know f of x at x equal to x1. And then to that, we just add the difference. Add something like f of x1 plus dou f by dou x at x1 times some delta x. We say that this approximates f of x2. And the smaller and smaller this delta x is, the closer and closer this f of x2 value is, right? And now if you want to find f of x at some other value of x, which is far away from x1, you can repeat these steps again, and again, many number of times. And the more refined the value of delta x is in each step, you will get a better and better approximation for f of x2. So this is Euler integration, and this can be implemented. You can think of implementing this using the skip connections of ResNet. But that's not the ideal application of it. But this is very similar to how ResNet learns the difference if you are unblurring a blurry image. Now, coming back to the case where we want to implement ResNet architecture for our neural network, let's first compare the architecture of VGG versus a plain CNN architecture versus ResNet. So this is what VGG had. It simply had 3 by 3 convolutions. LXNet had different convolution operations. VGG showed that all of that is not needed. We just need 3 by 3 convolutions repeated multiple number of times. Only thing is, here we are showing the architecture of VGG 19. In the previous last two lectures or 2 lectures before, we used VGG 16. But here you can see that this is the general architecture of VGG 16, VGG 19. And then if we have a simple 34-layer plain neural network architecture, it may look something like this. Now, if we have 34-layer ResNet, as this is the image from the paper, ResNet paper, you will also have these skip connections or these residual modules. And if you have seen in the context of ResNet, terms like ResNet 50, 101, 152, etc., it simply denotes the number of layers. ResNet 50 will have 50 layers. ResNet 101 will have 101 layers. So stacking more and more number of layers to form deeper and deeper neural networks. Now, before we look at implementing the ResNet in our 5 flowers dataset, let's just have a comparison of ResNet against the other 3 models that we have tried prominently. I'm not including SqueezeNet here, but I'm comparing AlexNet, VGG 16, Inception V1, which was GoogleNet, and then ResNet 15. So AlexNet in 2012 at University of Toronto, Alex, Ilyas Etskever, and Professor Geoffrey Hinton. Depth was 8. It introduced ReLU, dropout, and parallel processing using GPU. 60 million parameters this one had, and it got top 5 accuracy of 80.3 in the ImageNet competition. And it was the winner of ImageNet Challenge in 2012. VGG 16 in 2014 from University of Oxford. They had 16 layers. It was from a group called Visual Geometry Group or something like that. The main idea was you don't need different types of convolution filters. You just need 3x3 filters. It was huge model. It had 138 million parameters, but achieved 92.7% accuracy. Although it was not the winner, it was the runner-up. So they placed second. In the same year, 2014, Google introduced GoogleNet, which later got renamed as Inception V1. It had around 22 layers, 6.8 million parameters, very close percentage accuracy compared to VGG 16, 93.3. And in the same year, these people placed first in the ImageNet competition. Then in 2015, ResNet obliterated every single models until that point, introduced by Microsoft. They had 50 layers. So this was the deepest neural network up until that point that won the ImageNet competition. Their main invention was the residual blocks. In the Inception, the main invention was they had multi-scale convolution blocks. So initially they had a 1x1 convolution. In parallel, they had pooling operation. Followed by these operations, they had one more layer of 3x3, 5x5 convolutions. And finally, all of this multi-channel convolutions were concatenated into one single layer. So this allowed this 1x1 convolutions allowed the models to learn local features, whereas 5x5 convolutions, because you are looking at 25 pixels at the same time, allowed you to learn more global features. So this is why it's called multi-scale features. Now coming back to ResNet 50, it introduced the residual blocks or skip connections, which had 25 million parameters for the ResNet 50. It achieved 93.6% top 5 accuracy, and it was the first place winner in the ImageNet competition in 2015. So far, if you look at the number of citations, the ResNet 50, the paper associated with the ResNet has the biggest number of citations, around 270,000 citations. Now, if we were to implement ResNet in our code, where should we make changes? We just need to make changes in two places. So in the weights and biases configuration file, configuration part where we mentioned the project name, I just renamed the project to be ResNet 50, ResNet Flowers. That's it. In the architecture, which is a config parameter that we are not using, I just name it as ResNet, just so that somebody who's reading the code can immediately see that this is implementing ResNet. And of course, we are using pre-trained ResNet. So this is one part of the code where there is change. Another part of the code where there is change is in the module where we define the neural network. So we import from torchvision.models. This is from PyTorch. We import ResNet 50 weights. And this is the pre-trained weights of ResNet 50 from the ImageNet dataset. So these weights are being used in the models where we define models.ResNet 50 as our model. And then we freeze all the layers except the final layer, where in the final layer, we'll have 5 nodes because we are performing 5-class classification. And then everything else remains the same in the code. So basically, you might have noticed that in the last few lectures, the amount of change that is happening to the code is very minimal because we are trying different neural network architectures. So here also, exact same thing that we have been doing in the previous lectures we are doing here. Just changing the weights and biases configuration parameters so that we are logging the experimental results appropriately on the weights and biases platform, and changing the model weights, this model weight. So previously it was SqueezeNet weights. Now it is ResNet 50 weights. And then changing the model itself. We are importing models.ResNet 50. So that's pretty much it. And then after this, let's see the results. I'm sure you're waiting for this. I will show you the entire code. And but before that, I just wanted to show you the results. So the results are nothing but amazing. We have 97.9, almost 98% training accuracy and almost 95% validation accuracy after 50 epochs. So far in whatever we have done, this is the best model so far. And in fact, we have been doing this for the last couple of lectures. So in SqueezeNet, in the last lecture, we obtained very good training and validation accuracy, around 90% for training, for validation, and around 95% for training. And now we have around 98% for training and 95% for validation. Absolutely amazing. If you have been following this lecture series, you should feel so happy today because look at where we started from. When we started with the linear model, we were saying, oh, we are just getting 35-40% accuracy, where we should have been getting 90-95% accuracy. And here we are after trying different models. Of course, we can push this closer and closer to 100% accuracy with hyperparameter tuning, hopefully. But we are not going to do that because that will unnecessarily prolong the lecture. But I hope you already get the point. We have to use pre-trained neural networks for getting really good accuracy for images like this. We had to play with neural network architecture a bit to see which neural network architecture works the best for our particular data set. And not just that, we also have to perform some other hyperparameter tuning like learning rate and few other hyperparameters. If we do all of that, we can potentially get the best model for the task that we have in hand. So today is a great day for all of us because we have achieved the best model. This is the code. I'll be sharing the code file with you. So same thing that what we have been doing. We connect Google Drive and Google Colab. We import the required libraries. We define the weights and biases configuration. And when we run this block, it will ask for a weights and biases API key, which we can paste from the weights and biases website. We can get the API key, we paste it. And then we do data pre-processing. So we perform some resizing, which does nothing in this case because our data is already 224 by 224. But we perform random flipping and we also perform normalization. Our data set, which are the images, it's present in my Google Drive. So you can take a copy of that and you can define your own path. So this path leads to my Google Drive. In that, there is a folder called 5 flowers data. In that, there is a folder called flowers. And in that, I have training and validation folders separately. So you also have to do the same thing if you want to run similar code. So this is the only part in the code. A change will be there. Here, the project name you can change if you want. Otherwise, you can keep it as such. No need to change. But the weights and biases API key also will differ. You will have to paste your own API key. And then we load the ResNet 50 weights. We use that model for defining the neural network architecture, cross entropy loss as the loss function. Then we train the model. We print the loss and accuracy values after a certain number of epochs. And then here are the results. All these results are logged into the weights and biases. And from that only, I picked this plot. So this plot was actually taken from weights and biases platform so that I don't have to explicitly plot it. It's already available. So in conclusion, it's a happy day. ResNet 50 has really absolutely killed it for our 5 flowers dataset. Now, with that, we can wind up today's lecture. I hope you are having a good time in this course. We have been trying various models. I hope you are getting a very good mental picture of how computers vision evolved over the years before 2012, after 2012, all the way till 2016. You have a very good idea now. You have a very good exposure to what all different models existed out there, why they were introduced, what did it accomplish, etc. So please do feel very good about yourself because till this point now, we have finished around 13 lectures. So more than 1/3 of the course is finished. And you have been with me throughout this journey, lecture after lecture. So I feel so happy that you are here at this point with me. It's not an easy thing to do. So thank you so much. We will meet again in the next lecture. Take care until then. Bye.